protons are much heavier than electron. If electron is 9.1 times 10 to the negative 31st, these two are around 2,000 times greater or heavier than electron, if you want. As you can see, actually neutron is slightly heavier than a proton as well, just by a little bit, but still. The difference between proton and neutron is the fact that protons are positively charged. They actually feel electric force. Neutrons are neutral. They don't feel electric force. Both of these two are in the nucleus, while electron is outside orbiting the nucleus. Now you can see that I am using two different other units for mass here that are more relevant when we talk about nuclear physics. One of them is U, the atomic unit for mass, which for a proton and neutron is approximately 1, and for electron is approximately 0. So for example, if an element has like 6 protons and 6 neutrons and hence 6 electrons, you can say its mass is almost 12 U, because each proton contributes 1 U, each neutron contributes 1 U, and each electron almost 0 U. And then there is another way to express the masses, especially in the particle physics, among particle physicists, and that's in terms of a mega electron volt. If you want to know what the conversion factor is, this is how you go from U, the atomic unit, to the kilogram. So 1 U is 1.66 times 10 to the negative minus 27th kilogram. In order to find the relation between mega electron volts and the other two, you can use the fact that in relativity we talked about the rest mass and how it's related to like the energy. So if you consider like 1 U, which is equal to these many kilograms, and then if you multiply it by the speed of light, which should be 10 to the 8th. This is not 120 to the 8th, that's 10 to the 8th. You are going to get this much joules energy, and if you convert that into electron volt, you are going to get 931.494 mega electron volts. So that tells you 1 U, which is equal to these many kilograms, it's also equal to this much mega electron volts divided by C squared. That's the C squared that comes from the other side. Now note that there are some numbers that you assign to each nucleus. One of them is the atomic number, Z. That's the number of protons in the nucleus. Basically that defines what elements you are dealing with. The number of protons is the sole important thing when you are talking about the elements. If you change the number of protons, the nature of the element is going to change. You are going to have a different element, in other words. But if you are dealing with the same number of protons, but you change other things, you still are dealing with the same element. Then we have neutron number, which is the number of neutrons in the nucleus. And then when you add those two, when you add the number of neutrons to the number of protons, you get the mass number, which is the total number of nucleons in the nucleus. Now, what are nucleons? Nucleons are anything that reside inside the nucleus, basically protons and neutrons. So protons and neutrons are in general called nucleons. So what I'm trying to say is the fact that A, the mass number, is basically Z plus N. If you know the number of protons and number of neutrons, when you add them, you have the mass number of the system. Now usually we use this symbol to show these two numbers. So you have the chemical symbol for the element. You put the atomic number at the lower left side of the element or the symbol, and the mass number goes on the upper left side of the element or the symbol. For example, for aluminum, Z is 13, A is 27, and by subtracting these two, using the fact that A is Z plus N, you can say that this element has 14 neutrons. The other thing is, you can have the same number of protons but different number of neutrons inside the nucleus. So you are basically talking about the same element because you have the same number of protons, but the mass of that element is going to be different. For example, carbon. For carbon, we know that the atomic number is 6. That means there are 6 protons. You cannot find any carbon with 7 protons. That's a different element. But you can have carbon with different numbers of neutrons. Like the most common carbon is carbon 12, where there is 6 protons and 6 neutrons. But we can have carbon 13, carbon 14, which is a radioactive material, or even carbon 11. So if you look at these, you have the most common one, but then they have different. But we have different nuclei with different number of protons. So all have 6 protons, but this one only has 5. This one has 6 neutrons. This one has 7 neutrons, and this one has 8 neutrons. You probably know that these are called isotopes of the same element. So this element, like carbon, has 4 different isotopes. Or even hydrogen. Hydrogen, which is the smallest nucleus or element, if you want, actually has some isotopes of its own. So if you look at the regular hydrogen, which has 1 proton and no neutron, it's what we call hydrogen. But then we can have a hydrogen with 1 neutron. So it's still 1 proton, but then 1 neutron, and as a result the atomic mass is going to be 1 plus 1, which is 2. This is what we usually call deuterium. And then we can have tritium, which has like 2 neutrons and 1 proton. But in general, if you know what the atomic mass and the atomic number are, you can easily find the number of protons, number of neutrons, and number of nucleons in general. Now we talk about the radioactive materials tomorrow in the lecture.